everyone. We're going to go over lesson 4 today on Hess's Law. This is going to be our final new lesson of the school year. Let's take a look. Okay, as you can see on the screen, Hess's Law says that the overall enthalpy, remember delta H, the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps in the process. Now, that's a really fancy way of saying this. Sometimes a chemical reaction is either too difficult, too dangerous, too costly, or simply takes too long to do. So instead, we can perform different chemical reactions that might be easier, cheaper, and safer. When you do this, you can actually get delta H values for these different reactions and then add together those chemical reactions and their delta H values to get the delta H value for a reaction that might have been too dangerous or too difficult to perform. So let's take a look at this in practice. So let's take a look at our first example of a Hess's Law problem. This part that I have boxed in red, we're going to call this the target equation. This is the equation that you are trying to get from these three equations down at the bottom. Notice that I've numbered them 1, 2, and 3. So what we want to do is find parts of this target equation down here and then ask ourselves two questions. The first question that we're going to ask ourselves is the molecule on the correct side of the equation? And the second question that we're going to ask ourselves is, does the molecule have the correct coefficient? So this becomes like a puzzle. We're using these three puzzle pieces to try and recreate this target equation. So let's take a look at our first equation here. We have nitrogen combining with oxygen to produce nitrogen monoxide, which is over here. Now, if you notice, nitrogen monoxide, which is right here, also appears in our target equation. That's a good thing. We always want to try and look for molecules that appear in the target equation. We don't want to pick molecules that don't appear in the target equation, like nitrogen, or molecules that appear in multiple spots, like oxygen, which appears in both equation 1 and equation 3. That doesn't mean we're not going to use them. It just means we're not going to use that to decide our answers to these two questions. So going back to the NO, the first question that we're going to ask is the molecule on the correct side of the equation? So in this equation, NO appears on the right side. In our target equation, it also appears on the right side. That's a good thing. The second question says, does the molecule have the correct coefficient? So in our equation, it has a coefficient of 2. But in the target equation, notice that it has a coefficient of 4. So in this equation, we're going to have to multiply everything by 2, including our value for delta H. So what I'm going to do is I'm going to rewrite this first equation, but I'm going to multiply everything by 2. So instead of 1 nitrogen, we're going to have 2 nitrogens. Instead of 1 oxygen, we're going to have 2 oxygen. And instead of 2 NOs on the right side, we're going to wind up with 4 NOs, or nitrogen monoxides. When we double everything, we also double the value for delta H. So delta H is going to now equal negative, that part stays the same, 361 kilojoules. Okay, So now we've used equation number 1. We're not going to use that equation again. Now we're going to look at another molecule from our second equation and find it in the target equation. So if we notice, we have ammonia, NH3, that is in our second equation. That appears in the target equation. So the first question is the molecule on the correct side? Well, here it's on the product side, but in the target equation, it's on the reactant side. So we're going to have to flip-flop this equation. Reactants will become products, and products will become reactants. The other thing that you're going to notice is that we have a 2 coefficient, but we need a 4 coefficient. So we are going to multiply this by 2, and we're going to flip it. So we're going to multiply it by 2, and we're going to flip it. So multiplying this by 2 means we have 4 NH3. Flipping it means those 4 NH3 are going to end up on the left side, on the reactant side of our equation. Now, since that's our only product right here, that becomes our only reactant when we flip it and multiply it by 2. Looking at our reactant side, our left side, which is now going to be on the product side, we have to multiply this by 2. So 1 nitrogen is going to become 2 nitrogens. Our 3 hydrogens, because we're multiplying by 2, is now going to become 6 hydrogens. I am okay with you leaving the states of matter out when you rewrite your problem, especially if you're typing all of this up, because that's just a lot of extra typing that we can eliminate here. Okay, so if you notice, we flipped the reaction, so my product became a reactant, and we multiplied everything by 2. So 2 NH3 became 4 NH3, 1 nitrogen became 2 nitrogens, and 3 hydrogens became 6 hydrogens. So now for our delta H value, when you flip a reaction, that also changes the sign for delta H. So what was an exothermic reaction, meaning heat was given off on the right side, is now an endothermic. So that sign for delta H must also change. So the negative sign here is now going to become a positive sign down here. We didn't do this for the first one because we didn't flip reactants and products for the first one. We only multiplied it by 2. So we flip it and we multiply by 2. So that 91.8, which we had as our delta H value, is now going to be multiplied by 2. So we wind up with a value of 183.6 kilojoules. So now we're ready to take a look at our third equation. So we're not going to use hydrogen. We're not going to use oxygen. We are going to use water. Water appears on the right side in this equation. It appears on the right side in our target equation. That's the answer to question 1. So does the molecule appear on the correct side of the equation? The answer is yes. Second part. Does it have the correct coefficient? The answer is no. It has a coefficient of 2 here, but a coefficient of 6 up there. So we're going to have to take this equation and multiply by 3. So when we multiply the equation by 3, we're also going to have to multiply that value for delta H by 3. So 483.6, we're going to multiply that by 3. We're going to get 1,450.8. Since we didn't flip the reaction, we only multiplied it by 3. The negative sign here stays as a negative sign here. Once you have used all 3 of your reactions, you can add together all of your values. So let's take a look. First thing that you want to do is cross out or cancel out anything that appears the same way on both sides of the equation. Very similar to what you would do when you are looking at an equation in your algebra class. So if something appears the exact same way on both sides, it can be eliminated. For example, I have 2 nitrogens on the left side of my first reaction, and I have 2 nitrogens on the right side of my second reaction. I can eliminate these 2 nitrogens that are on both sides. Another thing that I can do, I have 6 hydrogen on the right side here, and I have 6 hydrogen on the left side here. I can eliminate those 6 hydrogen from both sides. Finally, if I notice, I have 3 oxygen on the left side and 2 more on the left side. In this case, because they're both on the same side, they won't cross each other out, but we can combine them together. So we're going to end up with 5 oxygen on the left side. Here's our arrow. We also have our 4 NH3 on the left side. Now let's look at what's left on the right side. We have 4 NO and we have 6 waters. Now earlier I compared this type of problem to a puzzle because just like a puzzle, we put together all of these different equations and we add them up and we get our target equation. 4 NH3 plus 5 oxygen gives us 4 nitrogen monoxide plus 6 waters. Now, when we do this, we wind up with a delta H value of, so now the last step is to take your 3 delta H values and add them together. So we have 361, which is negative, plus 183.6, which is positive, so we're not going to put a negative sign there, plus 1450.8, which is negative, and we wind up getting a final answer of negative 1,628.2. So delta H equals negative 1,628.2 kilojoules. So we have now figured out the delta H for this target reaction without ever performing that target reaction. We took 3 different reactions that when we add them together will add up to this target equation. And as a result, we figured out the delta H for the target equation using the delta H values for these 3 different problems. So what I would like you to do for homework is to try these last 3 problems, or 2 problems. We have 2 problems left, 3 problems total. If you have any questions, please send me a message through Schoology or stop by office hours on Thursday. I'm also going to post the answer key to them, and on the answer key, I'll make a note whether I flipped them, multiplied them by 2, or divided them, so you can kind of see where that's coming from. All right, thanks everyone. Have a great week.